Can you please update me about the timing? There was some confusion today. I got lost, and so the official start is still 6:30 your time?
Yes, sir.
Okay, so we have some 15 minutes left until the official beginning.
Yes, sir. Yes.
Okay. Now that we had surprises already, can we please use a minute to just check again screen sharing to see whether it works?
Oh.
I believe I understand now how it works, and I just would like to have a brief check.
Yeah. Okay, sir.
Okay, so first of all, I'm sharing the slides, so you should see the starting slide now. Can you see this?
No, sir. Mira, you're sharing,
Mira,
right?
remove your screen.
Can you stop sharing so that sir will test it once?
Okay, now I've stopped sharing.
Yes, sir. Can you start sharing?
Okay, I'm starting again.
Yeah.
Wait a moment. Let me see. Whiteboard. It doesn't allow me to share full screen. Interestingly, so anyway, so I'm sharing the presentation now.
Yes, sir.
So
Yes,
that
sir. The screen.
works? Excellent. Yeah. Okay, so then I stop sharing now and switch to another one. Where is my Zoom? Oh, actually, it's good to try. Suddenly the menu changes. That's interesting. Wait, I get you. So now sharing, I have to get faster with this. Sharing image and sound. And so now.
Yes, sir. The audio and video is visible.
Is both there.
Perfect.
Excellent.
Yes.
That's what I wanted to know.
Yes, sir.
Awesome. Okay, brilliant. So actually from my side, we are good to go.
Yes, sir.
So I would wait here until you call me on stage, right?
Yeah. Yes, sir. Vinod, sir, shall we start?
Yes, nice. Actually, we have to, what to say, Mira has to share her screen.
Sir, can you stop sharing so that...
Can you please stop sharing
yes,
your
of
screen,
course.
sir? Yeah,
sure.
Thank you, sir.
And we can play the promo video.
Absolutely. Okay, perfect. Thanks a lot for your support.
Is my screen visible?
Yes, it is on my side.
Is it visible?
Yeah, Harita,
yes,
Mira. Harita.
Okay. Good evening to one and all present here for the IEEE webinar series SAVANT 2.0. I am K.R. Harita, Chairperson of Antenna and Propagation Society from the Department of Electronics and Communication Engineering. We are very sorry for the delay in the afternoon webinar session. Let's start with a positive thought by seeing our SAVANT promo.
Reloaded. Version 2.0.
Thank you. Thank you. I hope this promo would have boosted your thoughts. Now I request Dr. C. Jnana Kausalya ma'am, Professor and Head of Student and Staff Affairs, to take over and address the session.
Thank you, Harita. Good day, Dr. Peter. You are able to hear me?
Yes, I can hear loud and clear. Hello.
Good day. This is Dr. Jnana Kausalya, Professor and Head Department of Electronics and Communication Engineering from St. Joseph Institute of Technology, St. Joseph Group of Institution, India. So I would like to extend warm welcome on behalf of St. Joseph Management and SAVANT 2.0 IEEE Organizing Committee to Dr. Peter, Professor at Jacobs University, Bremen, Germany. So, Professor, thank you for accepting our invitation, and your presence here today is of great significance to us. Welcome, Dr. Peter, and our respect and gratitude to our beloved chairman, sir, Dr. B. Babu Manoharan, Managing Director, Madam, Mrs. Jessie Priya, and Director, Sir, Mr. Sashi Shekhar, and Principal, Sir, Dr. P. Ravichandran, for their continuous support in the second series of SAVANT 2.0. Warm welcome and happiness to dear participants from various places, and we are deeply appreciative and grateful. Welcome to all, and sorry for the inconvenience caused in the morning session. So thank you all for your patience. And now the session is over to Miss Harita, IEEE Chair APS Society, to introduce the speaker of today's session. Harita.
Thank you.
Thank you.
Thank you, ma'am. Thank you, ma'am. Now I will be sharing few words about the speaker. Dr. Peter Baumann is a German computer scientist and a professor in Jacobs University for about 15 years, where he is the head of large-scale scientific information system research group in the Department of Computer Science and Electrical Engineering. He is a founder and the CEO of Rasterman GmbH about 17 years. Rasterman has been listed into 100 most promising big data solutions. He has received an Innovation Award in 2013 and Kenneth Gaddles Award in 2014. He has also been a winner in NASA WorldWind Europe Challenge in 2014. He has patented in database system for management of array. We are honored to have you here, sir. Participants, you can post your doubts in the chat box and the attendance link will be sent at the end of the session. Sir, now you can share your screen, sir, so that you can continue.
Yes, my pleasure. So, first of all, while I'm getting my technology ready here, let me express my gratitude for this opportunity, which reached me by total surprise. And once I learned more, I was deeply impressed about the high international level of St. Joseph's Institute of Technology. So I would like to extend a warm thank you to Dr. Jnana Kausalya for my invitation and introduction, but I would like to congratulate St. Joseph's Institute for this active and highly competent student body to set up such international webinars. This is by no means going by itself, and I'm really impressed by that. So you have a great student body. So with that, we came together via IEEE actually, where there is a very lively body in India and where I'm engaged as well. And so this gives me the opportunity now to come together, and that means literally, let's come together, and I'm very interested in learning about questions you might have or comments, discussions. So feel free to join afterwards. I'll be curious about what we can extend in the chat. For now, let me go to the screen that I would like to share with you, which is my presentation. And as that is coming up, we hopefully see that. I see that I need to reshare. The computer did not like that I resized the windows, so I need to go into that one more time. This is the technology fiddling component, but by now everything should be good. Okay, so you see it already, data cubes. That is the buzzword that keeps us busy in our research and also getting that into industry. So what's that all about? First of all, that is, as in this kind introduction has been presented, Jacobs University in the north of Germany. You get some impression here of the campus. And let me mention a detail here. We are by design international. Actually, we have the size of about Caltech, about 1,400 students, but actually we share 110 different nations, and the only language we have in common is English. So really everything on campus here is in English. So if you would want to come by for studies or for maybe some research exchange, you can absolutely survive here with English language. This is common to all of us. So I'm teaching here and chasing students through applied computer science and practical computer science topics. And in my research, as has been introduced, our group is working on scientific information systems. Let me be open here. There is a lot of research and business about OLAP and business data. I'm very much interested in science and engineering data. So we have specialized on these ones. And that has led us to looking at large-scale raster services or array databases, as it's called today. Here's a link that points to the website of my research group. I will provide the PDF later on. Yes?
Sorry to interrupt you, sir. Sir, can you increase your volume?
I'll try that. Give me a second. So is it getting better now?
Yes, sir. Yes, sir.
Okay, perfect.
Thank you, sir.
Good. Okay, thank you for the hint. So I will provide the PDF, and for sure it can be made available somewhere so that actually you can follow these links if you're interested. This work has found practical interest as we built something that meantime is called Array Database Management System. And so we have pioneered that in science, but then people got interested. And so at some time we established a company to achieve that kind of support that a university cannot give. That also has led us into standardization. And so today we are editing the big data standards, if you will, in the field of data cubes. I'll talk a little bit about this. But first, let's move on. So what I would like to try now is resharing and show you a little bit of an introduction to this. And I must stop sharing here. And I need to reshare. Give me a second. That's an exciting experiment here. And here we go.
We know our planet inside and out. At least that's what we think. After all, we monitor the Earth and its weather patterns from outer space. We measure the Earth's surface and peer into her deepest depths. In today's world of optimal hardware and intelligent software, mankind is reverting to the status of hunter and gatherers. Researchers from all over the world are compiling a vast and very valuable resource, data about our planet Earth. This data affords a new glimpse of our planet. The ongoing exploration of the world has entered the era of big data. But this development also harbors some big problems. Keeping track of the data, making sense of it, is one of the biggest challenges facing mankind today.
So, coming back now, you will see me getting more and more fluent while going here. This is actually the intro of a documentary that we produced together with German TV stations, and that was broadcast in German, French, and English. And with permission, we have the English version on YouTube. So it's a 1-hour documentary about big Earth data seen from the data perspective. And that actually Yes, sorry, it has caught me. So somehow my screen sharing is not doing what I want. So I first kill that one and I reshare. So this is the fight of a man against technology. And here we are.
ஹலோ.
எஸ் சார்.
என்னாச்சு?
இல்ல சார், நெட்வொர்க் இஷ்யூஸ் நினைக்கிறேன் சார். அவரு திடீர்னு கட் பண்ணிட்டு போயிட்டாரு. என்னாச்சு?
இல்ல அவர் ஏதோ வந்து வீடியோ காமிக்கிற மாதிரி மாத்தினாரு. மாத்தும் போது ஏதோ ப்ராப்ளம் வந்துச்சுன்னு நினைக்கிறேன்.
ஆமா சார். நான்
ஃபர்ஸ்ட் ஒரு வீடியோ காட்டினாரு, அதுக்கு அடுத்து வந்து இன்னொரு இதுக்கு வந்து காட்டும்போது ஏதோ வந்து ப்ராப்ளம் மாத்தி எதனா கிளிக் பண்ணிட்டாரான்னு தெரியல.
மெயில் அனுப்பிச்சிருக்கேன் சார். அவர் ரிப்ளை பண்ணுவார்.
இப்போ மெயில் தான். இப்போ கான்டாக்ட் நம்பர் இல்லையா?
கான்டாக்ட் நம்பர் இருக்கு, பட் இஸ் நாட் இன் வாட்ஸ்அப் சார்.
வாட்ஸ்அப் குரூப்ல வந்து நீங்க கால் பண்ணுங்க, வாய்ஸ் இருக்குல்ல.
I'll try sir.
Sanjana, you can do a duo, Sanjana.
What?
Google Duo. DUO.
Wait. It is streamed live, so.
Okay.
யாவ் மெசேஞ்சர்ல கால் பண்ணலாம். அப்படி இல்ல நீங்க வந்து வாட்ஸ்அப் குரூப்ல இருந்து வாய்ஸ்ல கால் பண்ணீங்கன்னா தெரிஞ்சிடும்ல.
Sir, they are trying, sir. They are trying. Just wait
okay.
for some minute. They are trying.
Sir?
Coming back. Hello, everybody. Can you hear me?
Sir?
It's my okay.
Hello.
What
I
happened,
can hear
sir?
you very faint.
Yeah.
Am I audible now?
Very, very faint. Very low. I
Oh,
can
can you
hear you.
raise the volume?
Yes, I can understand you.
Okay.
So I seem to have lost at some time. Zoom crashed here, but I couldn't realize that because I was full screen. I'm very sorry for that.
That's okay, sir.
I guess I'm connected right now. Can you hear me loud
Yes,
and
sir.
clear?
Yes, sir, you're clear.
Okay. So can you give me a hint on where actually connection stopped so that I know where to catch up?
You're showing a video on the fight between humans and technology, sir. And it
Okay,
got
so after
disconnected
the
from that.
video, it's okay.
Yeah.
That good. Okay, so then let me try again and I catch up. So I'm sharing. So give me a second.
Yes, sir.
I need to go back. Good. Okay. So just to make sure, this slide you have not seen yet, correct?
Yes, sir.
Okay. So I would continue here. And I do not maximize my screen right now so that I will always see when Zoom crashes.
Yeah, okay.
I'm really sorry for that. So actually, you saw documentation, a 1-hour documentary that you can find on YouTube as well. With permission, we have uploaded it, which we have done with German TV stations, based on the experiences with dealing with Earth data specifically. And so the idea behind these data cubes, as they are called today, is that we bring them all together, all these many different files into one object so that it can walk seamlessly in all directions, not just in lat and long. Something you can do with Google Maps, for example, but across all dimensions, in particular along time. And time series analysis is the killer application today, for example, in machine learning. So this is actually a concept that is used all over the place. As I said, we are mostly interested in science and engineering, where you find such arrays, as programmers would call it, in sensor, in image data, in model output, simulations, and statistical data. So you find that in life sciences, earth sciences, in space, engineering, and of course in management controlling, where OLAP has a long tradition already. So all of these form multidimensional data sitting on some multidimensional grid. As such, they form a fundamental information category actually. So sets is something that have been dealt with in databases since long. Tables resemble sets actually in relational databases. And then at some time we discovered, hey, we need to do more. So hierarchies came in, like for example, well, somebody said once a Boeing 747 is not an airplane, but it's 4 million parts flying in close formation. And these are described by hierarchies, putting the parts in relation. Graphs are extremely interesting in research, and they have many applications from small ontologies up to large Facebook graphs. And then there are arrays. So these arrays actually stand out in that the data all sit on a particular grid, and that actually is a property that we can exploit, and that makes them special. So we will find 4 different technologies actually supporting these 4 different information categories, according to what Michael Stonebreaker, a famous database researcher, has said. No one size fits all. You need to have special support for special information categories. Okay, what is that in arrays? Well, array analytics is defined as efficient analysis on such multidimensional arrays of a size orders of magnitude above the evaluation engine's main memory. So we talk about multidimensional arrays. We don't care about the dimensions. And we talk about the big data. If you can load it into your RAM of your computer, it's boring. That's not where we need new technology. It's when it's bigger. So you say, I have a large computer. I have a supercomputer with a terabyte of RAM. Okay. And I show you data cubes that have 10 petabytes in size. So this is where we need special technology in order to handle these, in order to have services on these big data. The essential property is the Cartesian neighborhood of these points, and we can exploit that. Whenever we want to access the red point, it's extremely likely that in the next moment we want to access the blue neighborhood points. So this is where we need to think about efficiency. There are secondary items like the number of dimensions, whether this data cube is sparsely populated or densely. And the operations actually, if we step back in terms of mathematics, it's vectors, it's matrices, it's tensors. So altogether we talk about linear algebra plus a little bit in addition. So that is what array analytics should do. And I can tell you that on the planet, all the different research groups that meantime have emerged, they have made impressive progress, but we are far from having reached a full goal here. Actually, it started way back with the beginnings. When we did that first, I told you that I'm coming from a database background. Database people were very conservative. If it's not tables, it's not databases. So it was not accepted for a long time. There were some thesis works that started and stopped again. Unfortunately, they were discontinued. But at some time, you see that a wave came up. More and more research groups and also companies, by the way, started working on data cube support for large-scale data management. Below you see some service that we did with a German remote sensing data center back in 2001. So the graphics is way not what it could be today, but in the background, we had a three-dimensional satellite image data cube, and we could query it. That gets me actually to Rasterman. So raster data manager is how it spells out, this funny name. The idea is we want to have raster data, so data cubes in SQL. Okay, SQL is nice and handy for querying data, but unfortunately not data cubes. So we said we need to extend SQL and we need to add primitives, we need to add operations that perform signal processing, image processing, etc. in SQL. Without knowing, we actually pioneered actionable data cubes with that. That's documented by publications and by patents starting 1990 or so. And then we underpin that with a massively scalable architecture, allowing analytics on such big data cubes. That's a full stack implementation. So from top to bottom, every component we have implemented the hard way. And today it's running on services that offer more than 10 petabytes. We have done more than 1000x parallelization, and we are doing planetary scale federations, which is what I want to show you live soon. And let me just mention in passing that this has brought us into standardization, and we are continuously receiving awards, as it has been mentioned in the introduction. So the open source Rasterman has seen more than 38,000 downloads meantime. And on the small map, you see where our visitors come from. So it's relatively known. And that has made its way into standardization. So since 2019, actually, part 15 of the SQL standard is multidimensional arrays. And that is exactly an extension that embeds arrays, data cubes, into standard SQL tables. So you first do a table definition where you have your green attributes, that's as normal. And then the red one suddenly is an MD array, that's new. So a multidimensional array of values, 5,000 by 5,000. Once you have told the system the structure, it can handle that. It can do operations. Like in the select clause, you do some computation on the pixels and you return the result as TIFF file. So you can do processing. You also can do filtering, as you see in the where clause. And so suddenly the red and green parts go together seamlessly. Why is that important? Well, because today this is separate. We talk about metadata handling and we talk about data handling, and they are distinctly different. So in the future, we have an opportunity to bring all that together into one seamless information plane. Actually, you can not only do simple things, but going up to essentially the discrete Fourier transform. Here's an example without going into details about doing matrix multiplication and doing histograms as such queries. So you see that we are scouting the way towards linear algebra support and hopefully at some time full linear algebra support in such array queries. Okay, here is another example of such a language. OpenQ Spatial Consortium, or OGC, is the standardization body that is concerned with location-based services in collaboration with ISO. WCPS, which stands for Web Coverage Processing Service, is actually a data cube analytics language that knows about the semantics of space and time. SQL NDA does not know. You can do anything. Human brain images, cosmological simulations, satellite images. It's generic and doesn't know about that semantics. Here we do know the semantics, so we can have latitude and longitude coordinates, and we can have timestamps. So that is the specific semantics coming in, and that allows us to deal, for example, with regular and irregular grids in space and time. Also, the syntax is a little bit different. It's more directed towards XQuery, because in that field, the metadata very often are in XML, where you want to use XQuery. And so we designed this language to be close in syntax to XQuery to allow a seamless integration. The mechanics underneath, however, when it comes to the bare data cubes, is the same. Okay, so now that we have seen that, I'm going experimental again, and I want to show you that in some example. Resharing Chrome. That's what I want. Okay, so that is some publicly accessible service, standards.rasterman.com. And this shows the standards actually in action, and it's based on Rasterman, so I'm just using that as a vehicle now. So you can come with many different clients, like for example, WCPS console, where you can send such queries, and then you get some results. So here's the query. I send it to the server, and I get back a result, which is just counting a single number. That's so the count here, that's boring. So let's take a number that returns some image. In this case, we have temperature, and that is colored now, so that we see the cold colors in blue and the warm colors in red. So that is done on the fly. If you want to see that more in action, here is NASA Whirlwind, which is a virtual data cube, sorry, a virtual globe. And we can run that in 3D by actually mapping it on the globe and slicing through time. So you see winter coming on the northern hemisphere, and you can dynamically add further data cubes to combine these. So that allows us to go three-dimensional X, Y, and time. For 4 dimensions, we prefer Microsoft Cesium because it allows to do what we see here. You can see height layers. So actually our data cube has been 4-dimensional, X, Y, height, and time. So we can switch on and off the height layers, and we can, give me a second, and we can change the footprint. So actually this query language you don't have to learn. We can just hide it behind a point and click interface. So here we go. Okay, that gives us an example of what I want to show you live. And here is something that I'm anticipating, and that is the federation part. Federation means we link together different services, and so we can actually ask for results from different servers. Here is an example where we combine in the WCPS language chlorophyll color with sea ice and with average temperature. We send that to Alfred Wegener Institute, which is a research center in the north of Germany. We can see the path of the query because several servers now had to work together to generate that image. That has found interest from countries far away. And so now we have, for example, something here that is connecting to Taiwan. So we combine Landsat and precipitation data and temperature data to do a vegetation forecast over Taiwan. We send the query from Germany to Taichung, And they have to ask back with another server in Germany in order to produce that result jointly. But we just see the result, again, using NASA Worldwind. And so here we get the vegetation forecast for the northwest of Taiwan. So how does that work? I mean, it's good to have that, because if you think how you do that today, distributed data fusion, you have to go to the different servers, get acquainted with the structure, find and extract data, download, homogenize, and then do the processing. That's now all done behind the curtains. So that is actually how we can do that with queries. I hope my Zoom will not die. Switching around all of that. I'm showing the URLs, by the way, so that you can also work with that if you want. I'll come to that in a moment, because we are doing now actually distributed processing. How do we do that? Well, the query semantics is known. This is the advantage, that we have a language that we have defined, that we know of, and that is codified in the standard. So our server knows what that means, and it knows in particular, oh, the yellow part I can do right away. I have dataset A. Oh, dataset B I don't have. But wait a moment, I have a friend in the cloud that has dataset B, so I cut out that subquery and send it over to B. So this is how we do cloud parallelization. And at some time we discovered, hey, we can do that also with other data centers. So the blue query, the blue expression, would be cut out and sent as a subquery to the blue house for processing. Actually, we are driving that so far as to go on board of satellites. We are on board a satellite of the European Space Agency. It's a CubeSat, and we have installed Rasterman there. And now we are just waiting to get access so that we can do data queue processing on board a satellite. So the semantics of the language allows us to do that. Now I'm skipping backwards a little bit because something I wanted to mention here. Some people will tell you, oh, we just take Python code and we ship it to the server. Would you really want that? If you have a server, would you want to get a Python code snippet from anywhere out there and you execute it blindly? The server executed while you're sleeping? I would not sleep well here. Actually, languages like SQL, query languages are tentatively designed to be safe in evaluation, so that a large class of denial of service attacks simply is not possible. With programming languages, if you just send the full code, that's not possible. So yes, you can do it, but maybe it's not the best possible thing. This is a principle that is very, very old. It has been introduced in the 1970s with SQL. Okay, behind the scenes, to be efficient, of course, we need to do a partitioning. If you have a petabyte of data, you cannot put it into one file. You will cut it into pieces, and actually, you could cut that in many different ways into pieces. So you can have tiles or partitions that all have the same size. That is the naive approach. You could stretch it a long time if you want to do long time series analysis. This way you optimize a time series evaluation by orders of magnitude. And in the end, you can have any arbitrary partitioning if you want. What we have done is we have made that available as a tuning parameter. So users will never see that in the query, but administrators can use that for configuring the tiling. So the insert statement has been extended with a tiling clause where you indicate the strategy of tiling and several parameters that you want to use, like compression, for example, and then the server just does it. Now, some people say, hey, wait a moment, that is way too complicated anyway. We don't need that. Especially hear that from tools that cannot do it. But wait a moment, look into OpenStreetMap. It also does tiling. Okay, it's on vectors, but it's still tiling for the same problem. If you are downtown New York City, you want to have very fine-grained resolution, so your tiles must be small to have a reasonable size on disk. Otherwise, they explode in file size. The Southern Pacific, on the other hand, you can put into one large blue tile because there are not so many streets there. So you want to have adaptive tiling, and it definitely makes a difference in performance, as we have measured. Okay, so the overall architecture of Rasterman looks like that. In the center, we have Rust Server, the workhorse that do distributed query processing without a single point of failure. The pixels can be stored inside a standard database like PostgreSQL, works like a charm up into terabytes. But then we implemented our own storage manager on file system, which is about 2 times faster than PostgreSQL because it's more specialized. And we were happy, and the data center said, forget it. Because they said, we are not going to copy our petabytes of data into a Rasterman database. Disk space is cheap, but not that cheap. So we had to learn something that is really scary for database people, to work on data that are not under our exclusive control. Today, we can work on any external archive if you just tell us the conventions of that archive, and then query processing works as usual. Users don't see any difference. Okay, that is all domain agnostic, as I said, SQL MDA. So no semantics of space-time. That comes in via an extra layer on top of it, which implements the OGC standards interfaces. So that is what the clients use that you have seen, and that is what the geo users like to see. So that is the overall architecture in a nutshell. Distributed processing we already had. And I showed you all that can mean when it comes to intercontinental data fusion, having location transparent federation. Yes, we saw that. Sorry, I'm talking too much. Actually, we are bringing that together in a European initiative that is called Earth Server. You can go to earthserver.eu, for example, where we have a couple of data centers already forming one big federation, and we are extending that continuously. Now, forget about the European. This is just how we started. Meantime, we also have Taiwan on board. So should that be of interest for some data center in India, please do feel free to contact me and let's talk about that. The advantage for us would be in the existing members, all your data could be made available for processing. For you, on the other hand, you have the European data available right at your fingertips, and that is a couple of petabytes of Sentinel satellite data. So we might benefit all from this, bringing together all our precious data. And by the way, also bring your client. You saw that already. We found out that not everybody likes query languages, mildly said. So thanks to the standards, actually, existing clients can be used. You saw some of them up to Python with Jupyter notebooks, for example, if you want. So people can stay in the comfort zone of their well-known tools instead of learning a new language. But this is also something we are working on. For example, we are working on a very tight integration with Python so that the Python code at runtime gets translated into queries. That's ongoing research work. Okay, here is a couple of things. Now that switching might kill my Zoom, I guess I will not want to switch there again. But I would encourage you to look at that, standards.rasterman.com. I showed you already. Inspire is another demo that has been done for the European Spatial Data Infrastructure Initiative that goes by the name of Inspire. And under Earth Server, we have webinars available that show all the aspects of handling data cubes, in particular from a standards-based perspective. So I'm skipping that here and just moving on to show you one sample project that we are doing. This is particularly dear to me because here we go into machine learning. And I told you about that, that this is one of the research avenues. So technically, it's about meteorology. We have weather forecasts and they work well for the flat areas of Germany, and they do not work well for the mountainous areas of Germany, simply because the mountains are so versatile in their different heights that the resolution of the weather forecast is not enough. Okay, so the idea is let's go for machine learning and use that to improve the rain prediction. Okay, now we have a big data problem. Machine learning works well, but not on the scale of data that we are talking about here. We are in the petabyte scenery. So the approach is to couple machine learning and array database systems so that we gain the intelligence of ML and the scalability of databases. That is something that we are doing currently and we are working on. And it's, I personally find that a very exciting research going into the future. To wind up, let me briefly summarize the standards. I have mentioned some of them. This is showing the DataCube standards that are in place currently in the field of science, of geosciences in particular. I mentioned Open Geospatial Consortium. They call it coverages, what models DataCubes. And so it's called Web Coverage Service, what they define as web services for dealing with DataCubes. In ISO, we have Technical Committee 211 that maintains the mirror standards 19123, and we have -1 and -2 there. -1 is the abstract standard describing the fundamentals. -2 is the concrete implementation schema. In a totally different compartment of ISO, in subcommittee 32, we find SQL MDA, the multidimensional arrays. And then on the fly, INSPIRE, that's the European Spatial Data Infrastructure Initiative. It's again about coverages and web coverage service, so that links back into OGC. What we try very much as we are engaged in all of these bodies to bring loose ends together and to see that concepts are compatible so that we don't have competing standards, but compatible standards. Okay, so let me summarize. Arrays are a key data structure wherever we look. In science, we find it as well as in engineering and of course in business. So arrays are one fundamental information category that are needed everywhere. And in the age of big data, we have big arrays. And if we want to serve this over the web, according to the principle of big data, they are too big to transport. So we need to ship the code to the data. We need to do analytics in the server, naturally. And that is the gap that we are researching on and we are trying to fill. Rasterman is our vehicle for that, for implementing our ideas. The core idea is have a high-level declarative query language, which allows for seamless integration with metadata to make access and analysis easier. And then underneath, we can do a lot of things like optimization, parallelization, distributed processing to achieve high performance. You see this distinction, clear concepts, and then implement those, but keep them independent. Fortunately, today there are DataCube standards in place that allow for interoperability across different products, be they open source or commercial. For the future, there are many interesting research items, and here are just two of them, handpicked. The one thing is, under the hood, we are working further on optimization. In this case, actually cost-based optimization already allows us to estimate the cost of an incoming query before executing it. We can do that locally, but actually this PhD student wants to extend that for federated queries. So queries that are executed across many different servers, we want to find the best possible distribution and balancing so that we get optimal performance. Okay, that's under the hood. That doesn't affect functionality. Functionality we address when we go to machine learning, because machine learning means we need to offer more in terms of linear algebra. What does that look like in a query language? How can we embed it without making it overly complicated? That is one of the research questions that keep us busy these days. And with that, well, let me stop here, take a deep breath. Thank you so much for bearing with me and also for your patience with these interrupts. I'm really sorry for that. I understand that right now we are still connected. Zoom is working without hiccups. That's great. So I'm really curious about questions or comments from your side. Thank you very much.
Yes, sir. Your session was really amazing to us. So shall we start the question answer session, sir? Sir, shall we start? Sir, am I audible to you?
Here.
Shall we start the question answer session, sir?
Sorry, I cannot understand you. Can you make yourself louder, please?
Shall we start the question answer session, sir? Shall we?
Yes, now I got you. Yes, please do so.
Okay. So the first question is, what is data cube in data warehousing? Could you get me, sir?
Okay. Do you have any way to get louder so that I can hear you better?
Yeah. Okay, sir. Okay. What is data cube in data warehousing?
Okay, I tried to guess what you said, and I understood data warehousing.
Yes,
So
sir. You want me to repeat it, sir?
it's just I almost cannot hear you. That's my problem. And it's not getting louder in any way. But I guess I understood it so far. So the data cube principle earlier, around 1994, has been adopted by business and administrative people in order to organize business data. What does that mean? Well, we sell goods. Assume we are a company selling food, then you want to know where you sell food. So whenever somebody sells, checks out at the counter, pays for it, then a billing record is sent into the headquarters, and this is collected. So at a particular time, in a particular subsidiary, a particular item has been bought. And that actually are 3 dimensions. That spans some 3-dimensional abstract space. And that space, then you can query. I want to find out how many bananas did we sell last month? How did the business in grapefruit develop? And how is that subsidiary performing? So lots and lots of questions that massage, that analyze the data cube. So in the end, it's pretty much the same like in our science and engineering data cubes. I see 2 main differences. Difference 1, these data cubes in OLAP, they are abstract. They have a business semantics, whereas our data cubes have a space-time semantics. Second, these OLAP data are very sparse. You don't sell every product in every subsidiary at every instance in time. Okay, we would dream of that, but it's not the case in reality. So you have a sales point here, you have a sales event there. In practice, you have about 3 to 5% of this data cube filled with data, and the rest is empty. On the contrary, the satellite images, and in particular the weather forecast, tend to be dense. So every point is captured. Every point in space and time holds a value. This makes the volumes way, way higher. And so we need different technology for that. So is that?
Yes, sir. Yes, sir. Fine.
Answering the question?
Yes, sir. Yes, sir. So shall I go to the second question? Shall I move on to the second question, sir?
I see something in the chat here. What is a data cube in warehousing? Okay, we had that. How is data stored in an OLAP cube? Okay, that is then the next question, yes. So actually, if you build up your data warehouse, you want to store it somewhere, and then you have 2 choices of technology. The one thing is relational OLAP. That means you use relational databases. The other one is multidimensional OLAP, or MOLAP in short. MOLAP is specific technology handcrafted for such business data cubes. So let's look rather at a more generic structure, relational OLAP. In relational OLAP, you simply pick every point, every sales event, and put it into one row in the table. So you record the product name, you record the subsidiary name, you record the price, and then every row in the table simply is a sales event. This is fine for sales events. This is a disaster for images. You would not want to store a pixel in a row and then have its X, Y, Z coordinates and do that row by row by row in a database. This would be a disaster. Nobody does that. It's inefficient. I mean, for the pixel, I know the pixels are lined up one after another. Why should I store the coordinates? So we have much more efficient ways for storing such arrays if they are dense. With OLAP data cubes, actually, it's perfectly fine because we have a sparse space. So we pick this and that one, store it together with the coordinates. And so actually the roll-up way of storing such sparse data in a table is just a nice compression technique. Works well if your data are sparse. If you have more than 3 to 5% data values, then actually it doesn't work any longer. And you need different techniques for that. So that's about how data are stored in a cube. As coming over with a low voice and I have difficulties understanding it, maybe we can put it into the chat and I will just work it off, if that is okay for you.
Yes,
So
sir.
the next one was explain spatial data cube construction and spatial OLAP. That is a good question indeed. It's somewhat different from OLAP in business. In business, as I said, you have your stores, and whenever somebody pays, a record is sent into the headquarters, and then it's collected in the database. How does that work with satellite images? Not that easily. So first of all, the satellite images have to be sent down from the satellite. Actually, there is only a short overpass window where we can receive data, because the satellite, how do we communicate? We need a ground station, we need antennas. We cannot have antennas all over the planet. So we have about 3 to 5 stations where a satellite comes over, and then we can receive data. So the satellite is keeping a mouthful of images, and whenever it's over some ground station, it sends them all down. Okay, now the data are down there. They need to be cleansed. Actually, cleansing is also an important part in business warehouses because data never are clean by themselves. So that's always a difficulty. Here we need to do a lot of things. Some pixels may have been lost. We need to do correction of intensity. We need to have auto rectification, meaning we want to get them all onto a map. They are normally distorted, so we need to undistort them. These are a lot of steps until they come into some processing level, as it's called, where we can do something meaningful. That's essentially something like level 1C or level 2, where it starts. Okay, then we have individual files, and they are put on a server. Unfortunately, as they come from the satellite, they don't have the right size. Trust me or not, I have seen TIFF files, image files of 100 gigabyte. That's not really appropriate. Sorry. So in order to make them suitable for a data cube, we need to cut them into pieces that are more handy. In our experiments, we found out that 3 to 5 megabytes is a good size. Now think about 100 gigabytes versus 5 megabytes. So it is worth reshuffling them. Others first did not do that, but all approaches I'm aware of that are doing data cubes do the same thing today. Then we have another problem. Such a satellite image is just a snapshot in time. So think about, you have one image. Here's the camera. Then you get a second image 1 day later, and another one 1 day later. Now this is like a cake. It's thin slices that you have. And each slice is one file on disk. Now going horizontally, cutting out something horizontally, that is easy, that is fast, no problem. But if you drill through vertically, that is if you do time series analysis, again, this is the worst thing you can do. Because for every time step, you have to slice through one file, you have to open one file. Open one file just to get out a single pixel. That is not efficient. Therefore, actually, for such spatial data cubes, it has turned out useful to not have such slices, but to have small cubelets. So actually, you have a small cube of 3 to 5 megabyte in a format like NetCDF, for example, and then you have lots and lots of such cubelets, and together they make up for the big data cube. So all of these steps have to be done, plus quite some more steps. As I said, it's a complicated process. And in the end, we try to make that as automatic as ever possible to make it easier for the data centers to offer that. And then in the end, the users can see the homogenized data cubes. So this was the keyword homogenized, underneath of which you find a lot of individual tasks to be done.
Thank you, sir.
So that's it about construction. I tried to make that more visible. Can you explain about spatial data cube for supporting data analysis in environmental epidemiology? Now, I can talk hours and hours about spatial data cubes, but I'm not in the position to talk about epidemiology. So I'm not really expert there. Let me give it a try. And disclaimer, I'm not an expert at this. I would guess that for epidemiology, you need to have data about diseases and their geographic distribution. In the end, you would like to have a map, as we have them now for coronavirus in Germany, where you can get maps of where we have a concentration of cases. So that is one map, and each pixel would contain the number of sick people in this place. Then you likely would correlate that with other data. You want to find out, does it correlate with humidity, with rainfall? Does it correlate with temperature? So actually you would want to overlay. So you take different data sets and you want to combine those. This is something that you can easily do, for example, with a WCPS language. We are doing that routinely. Actually, you saw examples combining different data sets to get more insights. And that allows you to get these insights if you have the data available. Problem will be, you have your epidemiological data available because it's your research field, but you will not have the satellite data because you cannot afford having 20 petabytes of data in your back office. So you would want to go to some data center and fetch these data. That is the tedious part. Just think about, how would you do it today? Do you know the data center? Do you know the service endpoint? Do you know their service and archive organization? All those make it tremendously difficult. And so we try to come in here and help that you just get easier to these other data that you need in addition. And this way you could fetch climate data from somewhere. In this case, maybe you would want to have ERA 5 reanalysis data. You could have satellite data like Landsat, Sentinel from Europe, but you also have Indian satellites on Earth observation. So bringing all of that together is supposed to make people's life easier. A standard database task, if you will. Okay, so much about my attempt to say something meaningful about environmental epidemiology. Let me know in the chat if I missed the point. Okay, let me move on. What is a data cube in data warehousing? So that's pretty related to what I mentioned before. Data warehousing is business data analytics or business intelligence, as it's often called. So we talk not about pictures about the Earth, but we talk about business events. So it's different categories, but it's multidimensional. That is the commonality. And so the data cube essentially is the same thing. What people in OLAP have also done is they have built up dimension hierarchies to allow you to zoom in and zoom out. This is something we don't need in maps because you can zoom out and in easily without that artifact. So in that case, it's even a little bit simpler. I know I'm dropping several keywords here without explaining them, but for the sake of time, I would keep it brief. If you find that I should explain some term, again, just put it into the chat.
Sir, am I audible to you?
I have received some private questions here, but they actually are the same as we had. Yes. Okay. So I cannot see any further questions in the chat right now.
Sir, am I audible to you, sir?
To the moderator.
Sir, am I audible? Sir, am I audible to you?
So I'm sorry, I cannot hear you at all now.
Sir, I'm audible to you?
Already maximum amplitude here.
Sir, can you hear me? Hello?
I can hear you very, very faintly. Let me try to understand you.
Sir, can you hear me, sir?
Right.
Okay, ma'am.
Okay, so I cannot hear anything any longer. So if there is something I can contribute, then maybe just type it into the chat window and I will get the message. I have the chat window open here. Okay, I'm told to wait in the meeting, so I stay online here. I'll be waiting.
Thank you, sir. Now I request Dr. Rohini ma'am to take over this session.
Thank you, Harita. Good afternoon, Dr. Peter, sir. Am I audible to you? Good afternoon, sir. Sir, am I audible? No, I think...
Ma'am, you can continue, ma'am.
Okay. Yeah. Good afternoon, sir. A very good evening to all. Myself, Dr. Rohini, Professor. It gives me immense pleasure to deliver the vote of thanks for this webinar on behalf of Department of ECE, St. Joseph Institute of Technology, since a group of institutions. Processed data is information. Processed information is knowledge, and processed knowledge is wisdom. First, I would like to thank our guest speaker, Dr. Peter, Professor at Jacob University, Germany, for his galvanizing speech on data cubes as a paradigm for serving big spatio-temporal data. Thank you, sir, for finding time and giving information on data cubes and its standards, advancements from 1D to 4D data with real-time examples, despite your busy schedule for the SAVANT 2.0 webinar series. Thank you, sir. My heartfelt thanks to our beloved chairman, sir, Dr. B. Babu Manoharan, for his consistent upkeep in conduction of this webinar. My sincere thanks to our managing director, ma'am, Mrs. B. Jesipriya, and our director, sir, Mr. B. Sashishekar, for their guidance in conduction of this webinar. I would like to express my gratitude, our principal, Dr. P. Ravichandran, for his support to conduct this webinar. I also thank our head of the department and IEEE chapter advisor, Dr. C. Gnanakausalya, and all other faculties for organizing this event successfully. A special mention of thanks to our student chair, Ms. Harita, and all other IEEE students for aiding in conduction of this webinar. Finally, I thank all the students, faculties, research scholars from India and other countries for their active participation in this webinar. Thank you all.